Welcome to the NPTEL course on building energy systems and auditing. Today in the last module, module number 8, which is based on the green energy and sustainability. In lecture number 38, we will discuss the BIPV and the solar thermal. So, in this particular lecture, we will going to cover the building integrated photovoltaic and the solar thermal energy systems and their application, particularly the application of the solar collectors. So, first of all, let us discuss something about the photovoltaic material. So, there are three types of material which can be implemented in the PV cells, and they have their own the positive and negative the factors. The first one is called the monosyncratic silicon, and we can also call that as a single crystal silicon. And the next one is the polycricentric the silicon, which is also called as the multi crystal silicon, which is actually based on the how it is going to prepare from the silicon base. In case of the monocentric kind of a silicon or the monocrystal kind of a silicon, we will have to do it from the wafer cut from the particular object, and in case of the polycentric silicon, we have to cut it from a block. The third one is called the thin film sections, which is bit costly and which is also has a variety of application, and that particular thing is based on some kind of a 3D printing kind of a thing, where the crystals and the PV cells are actually going to print over a particular thin film. And if you see this the conversion ratio, we have already discussed that one. The conversion ratio of the photovoltaic cell, which is ranges from 10% to 20% mostly. We are thinking of, or the things are going to be better in the future days probably, and the presently the crystalline photovoltaic, which is the poly and the mono centric, or those kind of the silicon PV shells are actually captured the market. Almost 90% of the market is captured by them. It is very popular. The life expectancy of the photovoltaic cell is about 30 years. It is depend upon lot of other issues also, but definitely the efficiency will degrade as and when it is going to be older. The energy payback is range from 2 to 8 years. That means, after 2 to 8 years, you will actually get back the amount of the investment you have made in the very first day. So, I have written down the three types of monocrystalline and polycrystalline and the thin film kind of the PV types, and there are some other parameters how it is look like. The first one, monocrystalline, is look like blue and sometimes it is gray in color. The polycrystalline is bright bluish and sparkled tone colored. Thin one is the reddish black color, and it is also very flexible in nature. It can become in a sheet kind of a form, thin sheet kind of a form. And the third column gives the module efficiency. If you see, the module efficiency is decreased from top to bottom. That means the thin film is having much more efficiency. In that much more efficiency in that sense that it is having the 6 to 8% efficiency, but probably for the kind of the harvesting kind of the situation, where per square foot of area it shows the higher. I mean, it is opposite, because the watt peak is higher for the surface area. If you have, if there is a slight difference between this module efficiency and the surface area of 1 kilowatt peak per meter square. Per meter square, the watt peak is higher in the thin, whereas lower in the monocentric one, but the efficiency, modular efficiency, is much more in the monocentric. That means, per square feet it may generate less, but overall efficiency, losses and all, will be less in the monocentric with respect to the thin. So, we will go along with this the modular efficiency, that is better to go, because finally that will be counted when we see any kind of the energy generation point of view. So, these are the visually, if you want to differentiate, it will be look like this: monocrystalline silicon. The polycrystalline silicons are bit of the dark in color, and there are very close the lines over there, and the thin films are similar looking the monocrystalline, but it is a kind of a very flexible in nature. So, now let us see the what are the parameters that this energy generation through a solar panels is depend upon. So, there are 7 to 8 factors. So, based on that, let us discuss. The first one is definitely the solar radiation. As you know, it initiated with the solar radiation. Today, if suppose the sky is overcast, no, it won't be generated that much amount of solar energy. So, radiation is one of the issues. Next one is the location and the orientation of the solar panels that we have discussed in the last class, the tilt angle and the towards south and the west, and the location is the latitude, and also based on that all the criterias the radiation is also depend upon, and also the duration of the day, and all these things are there, and different charts are available for how much kilowatt hour is available for different type of different locations and all, at least in India and some of the countries abroad. The third one is the degradation of the solar panel due to age. This is one of the thing that what we are just now discussing the earlier slide. The efficiency is maybe the current efficiency or the very new the material efficiency or the panel efficiency, but it has another watt peak. Initially the thin film may give you 17 kilowatt peak per meter square or so, but it has the overall efficiency is 6 to 7% or so. So, that is the degradation due to solar panel due to the ages or so, that is depend upon the what material you are going to employ and how you are handling that one. Sometimes it may be broken because of some mishandled or something like that in the rooftop or so. Maybe some kind of the cyclone or something like that, it may have some kind of a degradation, that is the external degradation, but during the ages or the due to the old ages of this particular panel because of the material over there. So, it has a kind of a degradation. So, based on that it is better to calculate the areas based on the modular efficiency, not from the watt peak per meter square or so. Next is the wind velocity. Wind velocity is also the different the velocities in the different time will definitely going to fluctuate the amount of the electricity generation. The temperature of the panel is another issue. Temperature of the panel, if it is increased, the electrons that the movement of the electrons is going to decrease. What we know from our the literatures and all, when I am not very much knowledgeable in particular in that one, because it is all comes down to the semiconductor physics. So, temperature of the panel is a issue. So, sometimes people are thinking of using some solar heater backside of the panels, so that the temperature can be reduced down, and also you can generate some kind of a heat. That is another issue. And this is one of the most important issue, because when the solar radiation is very high, it has a high potential to generate electricity, and that time the temperature is also very high, of the solar panel temperature is also very high. So, it may reversely affect the harvesting capacities also. The next one is the shading upon the solar panel, because of some parapet wall or maybe some trees nearby or maybe some building nearby, there may be some shade, and for that definitely it will be it will be restricted, the generation will be restricted. The dust accumulation over the solar panel, this is another issue. We have to clean it properly and regularly in periodical interval, so that dust is not accumulated over the panel, which will again decrease the efficiency of the panel, and that will reduce the electricity generation. So, now if you go to the building integrated photovoltaic, it is another type of photovoltaic, which is which is be applicable to the all facade of the building. So, I have written down the output energy over here is electricity, the application is offset building electricity consumption and export to the grid. So, it is mostly for the generation or regeneration. It is applicable in the high rise building, and specifically it is in the vertical facade to sun without obstruction is the specific requirement. Now, one thing is very clear to us that if I want to generate electricity and if I want to have more and more electricity, I have to increase the amount of panel area of the panel. So, if I go in case of the high rise building, as you know, the rooftop area is remained same. Okay, suppose it is a G plus 3. So, whatever may be the rooftop area for G plus 5 or G plus 7, the rooftop area will be the same. So, if I only bang on the rooftop area, then I can have a limited amount of the generation of the electricity, and based on the increment of the high rise building, I cannot cope up. My electricity generation through the solar through solar panels will not be high if I go high rise. So, only thing I can do that as we go high, we can the building will increase its surface area. So, if I can put the solar panels in the surfaces, all the 3 or 4 surfaces, potential surfaces of the building, then the amount of the generation will be also going to be high. So, for 3-storied building, it is maybe of maybe 9-10 meters. For 5-storied building, it is the 15-17 meters. So, as and when the building will be going higher, I will get more surface area, potential surface area, and I can have more generation which is needed for the to take care of the zero energy or something like that, to take care of the balance. But if I only bang on the rooftop solar AC, I cannot increase the surface area even if I increase the high rise the number of floors. So, that is why this building integrated photovoltaic is very much important to apply in this the high rise building to generate more and more electricity as and when it is go higher and higher to increase the surface area. The earlier one, the rooftop AC, what is there? It is also generating electricity, it is also the application from point of view, it is the offset building electricity is also, it is suitable for all type of building applications actually, and is also require the shadow free area, right. So, now in the building integrated photovoltaic application, where we can put even the rooftop installation are one of the type of the BIPV. Okay, BIPV is building integrated. So, even if it is a rooftop, it is one type of BIPV. So, what are the other type of BIPV? It can be in facade. So, BIPV system can be installed in the facade as a cladding or curtain wall or as a window. So, if I can use that as a cladding, I have two benefit. One is I can actually going to give a shade to my wall. So, that will actually going to be cooler, and the total energy that or heat energy which actually going to penetrate through conduction will be less. Of course, there is a catch point over here in between the wall and the PV cell, there should be a gap, and that gap should be thoroughly ventilated, otherwise that will trap heat because it is blackish in color, it will going to trap heat, and that may increase the conduction of heat. So, that is one of the issue. So, you may have some kind of a ventilation, kind of a forced ventilation system in between, but in general theoretically we can say that I can increase potential amount of surface area to generate electricity if I apply the BIPV system in the facade. We can also go with the externally integrated systems, maybe install in the balcony railing or maybe any kind of the porch, any kind of the area. Only suppose if I go for some portion of the areas of the parapet wall or balcony or some kind of a porch wall, chhajjas and all. So, that is also can be beneficial, because as and when you go high, your parapet wall may remain same, the area of parapet wall, but your amount of the balconies, amount of roof chhajjas, amount of some portion of the grilled work, or maybe some kind of the portion of the shaft that take care of your the water supply or the sanitary pipes and all those shaft length of the shaft or the height of the shaft is going to increase. So, only if I choose those areas, not the actual longer or the wider facade area, that also can be incremental as I increase the height of the building, and also that can fetch some kind of electricity. Why we can go to this externally integrated building systems or so? Sometimes architect may not like to wrap the whole building with the blackish color, the building integrated photovoltaic. It may not be good also, sometimes it may be look like not fitted for that particular area as a aesthetically or maybe culturally, that particular building may not take that one, may not be viable for that. So, in that cases we can go for those small areas and we can actually generate some kind of electricity. The carports, so the BIPV can be used in the carports. So, the car parking area, surface car parking area for some institutional building, maybe some kind of a mall where that can be available. So, over the car porch we can provide the shading, and with the shading can be provided with the BIPV, and this also be the same, the parking shades for all. And there are some few buildings in India also, the abroad also. I have one building from the India, U-Solar Cortel's data center in the Mumbai, which is about to be, I mean they told to be. I have visited their site and I have collected one photograph from the site, their website itself, and it is given as it has installed the solar PV of 863 kilowatt peak, which is very good and very high, and it has a capacity of it has actually installed 2466 numbers of panels, almost it has wrapped the whole facade. You see there are some mechanism which has been placed over there, some kind of the vertical girder kind of a thing which is movable, and that can be actually provided, because to clean those surfaces or so. It has 9 intervals, it has those, and it has a almost like very huge 1208200 the kilowatt hour per year generation capacity, which is quite a significant amount of electricity can be generated in this building. So, next one is the Johan Cruyff Arena A of Amsterdam. It is a football stadium where it has been, you can see again I have visited their website, and then I have taken this photograph from that. It is a international football arena where there are the big football matches are going on. It is a very popular stadium, and this stadium is it's kind of a indoor football stadium kind of a thing, and it has a panels, it has the solar panels in the stadium top, which is told to be given as almost 930,000 kilowatt hour electricity per year, of course, which is 10% of the total demand of the, because it is a indoor. So, it required artificial lighting to play football, and so 10% of the yearly it has been given. And I heard that this particular stadium is also sometimes when it is required, when it is off time. So, it is generated electricity, and that electricity is actually sending to the charging station, car charging stations. This is going to be prevent the emission of carbon dioxide entering to the atmosphere, equivalent to almost 180 car in a year or so. So, that is a considerable amount of reduction, and so these small the interventions if I can make, because we are also having lot of this kind of roof structure in our country. We have lot of maybe open stadiums, we have you have maybe we have how many, maybe 15 to 20 very good cricket stadium, around 10 football stadiums. So, those are open stadium, but it have some kind of the covering or some in the radially. So, in that also we can think of some kind of intervention of this kind of a BIPV, which can generate lot of electricities also. We have some other areas also, a lot of the bus stands are there, the railway stations are there, we have the airports are there. So, everywhere this large amount of these roofs are available, we can generally think of going on this kind of interventions. Different types of solar panel facade, we have there are still this is going on, this kind of the interventions. We can have a solar cladding that we have just now discussed. Photovoltaic cell directly integrated with the building cladding systems can be also thought of. We can thought of the transparent, the solar facade which can actually going to replace the windows. You can have kinetic solar facade which can actually change the orientation in different angle in the different time of the day. We can have the solar shading systems, we can have a adjustable kind of a shading systems again towards the sun angles or so, and that will give shade inside and also harvest some kind of electricity. We can have a ventilated photovoltaic which have a kind of a gap in between and then it can be ventilated through that. So, next let us go to the solar heating, which is another application of the direct application of the solar power or the solar electricity. The output energy is heat, not electricity, it is a heat. So, hot water I am going to generate, I can generate the low pressure water or so, the low pressure steam sorry, and then we can apply to the domestic hot water supply, we can use for the laundries, for the some cleaning operations, hospitals, hotels and all. And then we again we require the very the shadow free rooftop. So, this is the circuit diagram or maybe the system diagram of this kind of the solar the heater tank. So, there would be the hot water tank. I may say it is not only hot, it may be initially it may be a cold water tank and then gradually the water can be the temperature of water can be heated by some circular loop. So, it admits some kind of a cold water to advance to the solar collector. Solar collectors are some kind of a PV panel which is not look like a PV panel, but it has a two types we will discuss later. So, solar collector will absorb the solar energy from the solar radiation and the circulation of the water which is cold water now can be little bit temperature can be little bit high and it return to the system and again it will be circulated based on your speed or whatever may be your pump efficiency, and after certain time when the temperature reaches to a kind of the design temperature level, you can take that hot water to the supply to the different part of the building in your hotels, in your hospitals or maybe in your the housings. So, in the solar collector there are two type of solar collectors. So, you see it is a drum is attached to the solar panel. So, that means this is a kind of a solar collector. The first one is called the flat plate collector FPC, which is a kind of a dark box kind of a thin box kind of a thing which is transparent cover, and through that cover below the cover there are small pipes are there and then the water is moving through. The second one is called the evacuated tube collector. It has not a flat kind of a sheet, it has a the series of the tubes, and these tubes are having a inner and the outer shell, and these two are the technology is such a way that it actually the transfer the photons the radiation energy to the heat energy directly to the water or any fluid inside it, So, it is called ETC. Now, evacuated tube collector are considered to be the more efficient with respect to the flat plate collectors. So, how do we design the system? So, as I know there is a supply side. In the supply side, who is going to supply the energy? The solar radiation. So, what I have to do? I need to know the solar radiation intensity. So, for a particular day I need to know the kilowatt hour per meter square per day, how much is the solar radiation. Of course, that is available. We have seen in the last the lecture that it is available for some typical the cities in India. So, I can collect that one, and I can also find out some I can also know that this much area of the collector I can give some in meter square. So, this is the supply side. So, in that again I need to know the what is the collector efficiency. Collector cannot give you the 100% efficiency. So, FPC has little less efficient. So, the flat plate collectors are having 35 to 60% efficiency, whereas the evacuated tube collectors are bit more efficient in nature. So, it has a 55 to 75% of efficiency. So, this initial the solar radiation I, the collectors area A and the efficiency if I multiply, then I will have to have the supply side equation ready. in the demand side radiation, what I demand to increase the temperature of water. So, I need to know how much the amount of kg of water I have to handle per day. So, that I need to know. I need to know what is the ambient temperature of the water. So, normal temperature of the water that particular day or that particular month, average temperature of the water in that particular month, because winter month it will be little low, the summer it will be little high. So, that I need to know. I need to know what should be the hot water temperature TH, how much temperature I require to increase the temperature. Maybe I can get 20 degree temperature, I need 60 degree temperature water. So, this what is this 60 and what is this that is 20. So, ambient and the hot water temperature I need to know, and also I need to know the specific the heat of capacity of the water, that is for 4182 joule per kg per degree C. So, these are three, what are the three? This mass, the specific heat capacity of the water, and this delta T, the temperature difference, are the demand side the parameters, and I can multiply them also and I can equate them. So, I can equate them and multiply them, then let us see what can be the unit balance in between these two. So, if I take this one, the first one, the unit of the I, that is the solar radiation is kilowatt hour per meter square. It is for a day I am going to calculate, multiply with the meter square gives me the kilowatt hour is the unit in the supply side. Please remember that this eta, the efficiency does not have any unit, because it is unitless. In the supply side is this, and the demand side has 3 again. The mass is in kg, the Cp is your specific heat is joule per kg per degree C, and delta C, the delta temperature, that is the change of temperature is your degree C. So, finally, it is joule. So, in the demand side it is joule and the supply side it is kilowatt hour, which is also joule, but you have to relate that one by this the transformation factor, because 1 kilowatt hour is 3.6 megajoule, and which is 3.6 into 10 to the power 6 joule. So, by virtue of that I can equate this the supply side and the demand side, and anything unknown in between them I can easily find out. So, let us go to a problem solving. So, I have a institute guest house located in Pune, and it has a 25 double bedded room, 25 double bedded room, and I have to install a the solar rooftop heating arrangement to get daily water supply for all my guests. So, all my guests, and it is estimated that each person will require almost 5 liter of hot water at 80 degree centigrade. So, I am going to supply per person 5 liter water for this guest house, which is having 25 bedded double bedded room, 25 numbers double bedded room at a temperature of 80 degree, right. The design of hot water solar heater, sorry, not hot water, solar heater should be incorporated the monsoon and the winter season. The data are given below. So, data for the monsoon time and the winter time in the August and January in Pune is given below. So, what are the data? The solar radiation in kilowatt hour per meter square per day is given as monsoon is 3.49 and winter is 5.04. Whereas, the ambient temperature of the water mostly in and about in monsoon time is 25 degree and the winter time it is 20 degree. So, I have to actually see or do a comparative study or assessment based on which type of technology I am going to do, this FPC or ETC, and based on that, and we have to definitely assume some further suitable data. So, let us go with the demand side. What are the demand? Demand is I have 25 rooms, 2 beds. So, almost in a full house condition I have almost 50% in my guest house, 50, and 5 liter per day, that gives me 250 liter. I am assuming that 10% extra consumption maybe that is good to do, and so that means I have to prepare for 275 liter per day, which is equivalent to 275 kg of water, because 1 liter is equal to 1 kg. I have Cp with me 4182 joule per kg per degree C, and also the required the hot water temperature is 80 degree C. For both the season I required 80 degree C, but the ambient temperature different. Now, the ambient temperature in monsoon and the winter are different for these 2 months 25 and 20. So, I found out for the monsoon month how much is the my demand. So, what I did is that the delta T is 55 for the monsoon season 80 minus 25, whereas in the winter season it is 60 degree 80 minus 20. So, M into Cp remains same for both the seasons, only delta T changes once it is of 55 and once it is of 60. So, this joule I have calculated, and definitely the winter season it is much higher amount of energy I require. Next, let us go to the supply side condition. In the supply side, who will going to supply me? The solar radiation is supplying, and this solar radiation is again having a fluctuation. So, monsoon is 3.49 and winter is 5.04 kilowatt hour per meter square per day. So, in case of the flat plate collector, now let us come back to the two type of collector differently, take the things differently in the supply side, because the efficiencies are different. I am assuming a FPC flat plate collector efficiency as 50%. So, my supply side equation is I into A into this efficiency eta, where A is unknown to me, that is my design, how much area I require for this particular collectors I have to find out. So, in monsoon I have multiplied 3.49 into this area is unknown to me, 0.5 is the efficiency and this is the conversion factor, 3.6 into 10 to the power 6 is the conversion factor. Similarly, winter the changes is this only, this is the change, instead of the 3.49 I have used 5.04 kilowatt hour per meter square per day for winter. So, these two are the two different number for the demand side, and now I can equate them. Of course, sorry, let us go to the evacuated also. The evacuated base collector I am assuming a efficiency of 70%. So, I have done the similar calculation with monsoon and the winter, only change will be the efficiency 70% over here and 70% over here, and rest all the data as per the monsoon and the winter will remain same. So, I get two different figure in joule. So, now my supply side and the demand side, both the part of the equations are ready, only unknown is the A. So, I can find out the A. So, first what I did, I first estimate the collector area from the FPC point of view. So, supply side and the demand side equation I have equated. So, this is the demand side side that we have generated in the very first slide. This is the second slide generated, the supply side energy equation is generated. I have equated to them, this is the equation, and then I got the areas. I got the monsoon areas. Monsoon time, if we want to harvest, you require almost like 10 meter square of the area, whereas in the winter time it is little less areas required, 7.6. Please remember, in the winter time solar radiation is higher, it was 5.04, and monsoon it is lower 3.09, that is actually playing the role. Of course, you may say that in the monsoon time temperature is higher, the ambient temperature of the water is higher, whereas the winter it is low, but still here what you see is that winter you require less amount of the area, monsoon you require more amount of the area. So, we may go with the whatever maybe you can go with some kind of averaging, or if my initial investment is applicable to that, I mean I can go for a 10 square meter, I will be really I do not have to bother anything, I can run the things with a normal way. Otherwise, in time of, if I go with 7.6, a monsoon time little bit extra energy I have to put in through electricities or so to get that much amount of the temperature. So, next let us calculate the collector areas for the evacuated tube collector. Similarly, I did it and I found the areas like this. And now the thing is that evacuated tube collector, you have to find out not only the area, the number of tube. So, the length of the tube varies from 5 feet to 8 feet, which is 1500 millimeter to 2400 millimeter. Diameter of this tube is varies from 1 inch to 3 inch, which is 25 to 75. I have assumed for this particular problem as 6 feet long tube with 2 inch dia, which is 1800 millimeter, and 50 millimeter, which is the area. So, I have found out the area, and in the areas because it is the area of the cylinder, not the surface of the cylinder, but the projection area of the cylinder. So, the diameter and the length will going to multiply. So, that gives me 0.09 meter square, and I can find out the number of tubes required for the monsoon and the winter season by dividing that area of by the area of the evacuated tubes. So, only thing is that there is again a small typological error, it has to be ETC area, not FPC. FPC was the earlier one. So, that is all for today's lecture, and that ends the lecture of the solar one. So, what we have understood from here is that solar energy can be generated through the building surface and other type of application on the solar PV. Solar energy also can be directly used for the heating application in the building, and we will go to the next with the other two type of the energy, RE energy, renewable energy in the next slides. Thank you very much.